Hello, my name is Jacob Grubb. I'm here to present the paper Improved Classification of Medical Data Using MetaBest Feature Selection for the 42nd Annual International Conferences of the IEEE Engineering and Medicine and Biology Society in conjunction with the 43rd Annual Conference of the Canadian Medical and Biological Engineering Society. The initial goal of this research was to find attributes or features that could be used to classify certain medical conditions. These conditions included current smoking, self-reported diabetes, regular NSAID usage, light alcohol risk, death, and self-reported stroke. To this end, we use the regards, or Reasons for Geographic and Racial Differences in Stroke dataset. This was a dataset of medical, social, and economic data of approximately 30,000 participants between 2003 and 2007. Initially, we cleaned this dataset by normalizing values between 0 and 1. We removed features that were missing large amounts of values, and where features were missing small amounts of values, we would fill them in with the average of the remaining values. We also created a new feature called light alcohol risk that was based on the biological sex and the number of alcoholic drinks per week. The final dataset that we used contained a total of 65 features. One of the main problems we encountered when working with the regards dataset is a problem shared by many large datasets: too many features. Datasets with a large number of features take much longer to classify and can be misrepresented by noisy data. To solve this problem, we should take a subset of our features that can accurately represent the data. It is there that our problem presents itself. How can we select an appropriate subset of features without testing every possible combination? To test every possible combination, we would find ourselves with an exponentially growing number of subsets, an unviable situation for datasets with a large number of features. The solution to this problem is studied in the form of feature selection, or, as Liu 2011 describes, feature selection is the study of algorithms for reducing dimensionality of data to improve machine learning performance. So, our goal reiterated. We want to select a subset of our 65 features, either maintaining or improving our current classification rates. We analyzed two different forms of feature selection: sequential forward selection, which is a greedy methodology relying on building a subset of features one at a time, testing each possible subset with a classifier or wrapper method. These classifiers include logistic regression, naive Bayes, and random forest. Alternatively, we have correlation-based feature selection subset evaluation, or CFS. These identify features that correlate highly to the target but not to one another. For this, we evaluated best first, evolutionary search, and minimum redundancy maximum relevance, or MRMR, for our experiments. Next, we need a consistent metric for evaluating each feature selection method. We found the ROC-AUC, or the Receiver Operating Characteristic Area Under the Curve, to be the best metric for our purposes, as it was both easy to implement and more descriptive than accuracy alone. If we're going to be testing the effects of feature selection on classification, we will need a control case to compare. For this case, we used a feed-forward neural network with the hyperparameters shown on the screen. The set of all 65 features is fed to this neural network, which then attempts to classify the target attributes. The test cases are executed in a neural network with the same hyperparameters as the control case, but with a subset of the 65 features as generated by a feature selection algorithm. By comparing the performance of the testing neural network with the control neural network, we can determine the effectiveness of a given feature selection algorithm. The results for each of the 6 feature selection methods on each of the target attributes are shown on the right. Bolded results indicate the best feature selection method for each attribute. At this point, we combine the improvements from each feature selection algorithm into a single ensemble method, MetaBest. The goal of this method is to automatically select a feature subset, given the results from the component feature selection algorithms. In addition to providing a subset list of features, MetaBest provides a ranking for each selected feature. By weighing a particular feature's influence by the number of times that feature was selected, as well as the AUC improvement given by each component algorithm, we can effectively rank each feature's correlation to the target attribute. We first assigned each feature selection method a score S, ranging from 0 to 1, where B sub method is the AUC gain for the target attribute generated from the given feature selection method. B sub target is the best AUC gain for the target attribute across all feature selection attributes. The goodness score of a feature G is then given by M, the number of times a feature appears across all subsets, divided by the sum of each S score of a feature selection algorithm that used that particular feature. A sub n is a binary value, 0 or 1, indicating that that feature was selected within the nth feature selection algorithm. The resulting goodness value g is then compared to a user-given threshold, t. If a feature's goodness value exceeds the threshold, then the feature is added to the subset and ranked with the relevant goodness value. If the feature fails to meet the threshold, it is then dropped from the subset. By adjusting our goodness threshold, we can generate larger or smaller subsets of features. We tested our neural network with feature subsets generated by a range of threshold values as shown on the right. By comparing the AUC gain of the feature subsets generated by the MetaBest method with a control case of no feature selection, we show improvement when attempting to classify the given target attributes. We found that a threshold value set between 1.0 and 2.5 was the most effective for our testing purposes. The exact threshold peak varied slightly per attribute, but still fell within these bounds. Within the threshold bounds given above, we also found that MetaBest would perform slightly better, plus or minus 0.0005 AUC, than any of its component feature selection algorithms. MetaBest also consistently outperformed the control case of no feature selection within these parameters as well. By using the feature subsets of other feature selection algorithms and weighing them by the AUC improvement, we were able to create an ensemble feature selection method that performed better than any of the component algorithms. By assigning each feature a goodness value g, we are also able to rank the selected features in order from most to least correlation to the target attribute. Overall, we found that our MetaBest method would create feature subsets that would yield classification AUC similar to the component feature selection methods, but with an average of 2.33 fewer features per subset. When working in datasets with large number of features, such as regards, being able to generate subsets of attributes with better classification rates and fewer features is a valuable tool. MetaBest is our attempt to create an ensemble features selection method, and we have found that it performs slightly better than any of its component algorithms, making it a worthwhile method. Thank you for your time.